Okay. Um, Good. So yesterday we had like a very soft and informal introduction to what is a manifold, and today we'll try to tighten that up slightly. There's really no limit how much we can talk about it because differential geometry is a full semester course, and we can't possibly do that here. So we'll have to skip some of the details, and on the classroom page I have given you some links where you can find the details if you're interested. Okay. So based on what we said yesterday, we want to start with some kind of space and make it into a manifold. The problem is if it hasn't been made into a manifold, what kind of space is it in the first place? And the answer is it's a topological space. Some of you may know what that means. If you don't, it will be enough for us to just imagine this to be some set of points which comes with a concept of open sets, which is a natural concept. These are sets in this which help us to define continuity in a certain way. Okay, and well, just let's call them open sets and let's treat them as a black box until we need to use some properties of them. Okay, so it's a space which can be covered by such sets, and if you take enough sets and take the union of them, you'll get back your space, which is after all, ultimately any space is a set of points. So there are some preferred sets in it which are called open. We'll quickly understand what are the open sets of interest to us, but this is an abstract notion. Now we want to go from this to a differentiable manifold. And this one is quite straightforward. Based on our discussion of yesterday. For this, we first of all have to redraw our topological space here. I'm sorry because I ran out of space there. And we just pick one open set and another one called, let's say, O1 and O2. And I assume that they have some overlap. Okay. Then of course by repeating this, I can extend this, what I'm going to say, to all the open sets. Now yesterday we said that on each patch of the manifold, we use that word patch, we set up some coordinates, and on different patches we set up different coordinates. Okay, so let's draw using arrows. Let's show what that actually means. It means that from this patch O1 I have a map. The map is called phi, and the image of the map phi of O1 is an open set of some Rn or Rd, where Rd always I used to mean Euclidean space. Okay, how should we think of this? Well, when I assign coordinates to a patch of some curvy space, in my mind I'm taking a sheet of paper on which I have already drawn some x and y, and I just paste it there. Okay, this map is the pasting map. Yesterday we imagined the coordinates as living on the manifold. Now we have taken the coordinates somewhere else, and there's a pasting map which actually pastes them. That is the map phi, and the map works in both directions. It's a completely invertible map. Is that okay? Already some puzzlement. This is the formalization of a coordinate patch on this subset of the space. Now I have another subset of the space. So this map is called phi 1 because it's taking me from O1 up to some subset of Rd. This is another set O2, and there will be a map from here which called phi 2, which takes me to phi 2 of O2, which is also a subset of Rd. And when I say open subset of Rd, that's very easy to define. You probably know that in Euclidean space, this you might have learnt in calculus, you know what is an open interval rather than a closed interval. Open interval in a line is just a segment of the line which doesn't contain its endpoints. These are important for the precise mathematical definition, but most likely in this course, this business of open will not matter very much, but it is important for things to be open. So open interval is just a segment of real numbers which doesn't contain its endpoints. What is the generalization to, let's say, 2 dimensions? It's quite simple. It's a sphere which doesn't contain its boundary. And we just keep generalizing this. Okay, is the set of, okay, so let's give an definition of an open set in Euclidean space. Set of a subset not including its boundary. And in one dimension, there's really only one way to do it, which is to have an interval. But in 2 dimensions, you can have any kind of shape as long as that 2-dimensional shape doesn't include its boundary. In 3 dimensions and so on likewise. Okay. So for example, in 2 dimensions, it would actually, R2 is just this space. And the open set could be anything like this. But just imagine that the boundary is a dotted line. So it's the set of all points inside that. That's all we need. Okay. This just avoids certain problems, and as I said, we won't encounter those problems to start with. So don't focus too heavily on the word open. So I have these coordinates, these points have been mapped to a subset of Rd, and these points have been mapped to a subset of Rd. And notice that the map phi1 acts on the whole of O1, everything in O1. The map phi2 can act on everything in O2. Now there is this shaded overlap region. In this region, both the maps phi1 and phi2 can act because they are defined on, one is defined on O1, other is defined on O2. So in the overlap region, I have both maps. And now I can do a clever thing. The clever thing is, let me start here. I'll use the inverse of phi, but I'll only use it from points here which map backwards to points in the overlap, and from here I'll use phi2 to go there, which gives me a map between phi1 and phi2. And what is this map? It's precisely what we called a coordinate transformation yesterday. The key difference from yesterday's discussion is that I put the coordinates out where I can see them, and this map between this subset of Rd and this subset of Rd is just a map between real numbers. So studying this map only involves ordinary calculus of multivariables. It doesn't involve anything to do with the curvature or the weird behavior of the manifold. So in some way, this map allows us to forget the manifold and write functions. So here, if the coordinates of this part of Rd are xi and the coordinates of this patch are x prime I, then I get functions which are supposed to be invertible between xi and x prime I. So it's just the formalization of what I said yesterday. And as I want to emphasize, the real problem is how can I do physics on a curved, on a general manifold when I don't have simple things like a unique coordinate system in which I can differentiate and integrate. I don't even have a unique coordinate system on the whole space. We argued that yesterday. So I couldn't in principle do anything. The reason I can do something is that I cover it with patches on every overlap, and each patch gets mapped to a piece of Euclidean space. These are my coordinates. And then each set of coordinates get related, but only on the overlap, so that I can freely go from one to the other. So if I had a physical system which went from here to here, like a point particle, which we'll study in a few minutes, which goes from this point to this point, then I use the one coordinate system up to here. Then anywhere here I change to the two coordinate system, and then I continue there. But what I'm really doing is I'm always using this. Another way of saying it is that a sailor who's sailing on the curved surface of the earth is never looking at a curved surface in the room where they are steering the ship. They are looking at maps which are in a book, which are flat sheets of paper. These are the flat sheets of paper. This is the earth. Okay. This part of the earth is described by one flat sheet of paper. This part is described by another flat sheet of paper. Also, I don't need the whole sheet. I just need a part of it, right? The map doesn't have to extend to the edge of my sheet. It just has to cover some part. And the sailor uses this map when they are here and uses that map when they are there. And they have the ability to go between the maps when they are in the region of oval. This is the overall conceptual idea behind a manifold. There was a question.
Are we doing it on the tangential space, technical space?
Yeah, I haven't defined the tangent space yet, and we don't need the tangent space for this construction. We are actually mapping points of the. We haven't even talked about vectors yet.
But in a manifold, like let's say point P,
yes.
then you have to define that tangential space before you define this phi of O1.
Why? Phi is a map from points to points. I don't need any tangent space to define a map from points to points. Given a point here, it gives me a point here, which is the coordinate of that point. Given another point here, it gives me a point here, which is the coordinate of that point. No mention of tangent space. Tangent space comes later. In this map, technically, this is what is called a homeomorphism, which is an equivalence of open sets in topological spaces. But we don't need to know that. Yes?
So the phi functions are our coordinates, really?
The phi functions are functions, they are not the coordinates, their image is the coordinate. The way to think of it is the phi function takes an argument which is an abstract point of an abstract space. That point doesn't have any number associated to it, it's just a point. As I emphasized from the beginning of this course, a point has a certain reality which is independent of what number I assign to it. For example, a point on the earth, this point is this point, no matter what coordinate system you may want to use for it. It is the same point. So that's this. This is a space of abstract points. Phi simply takes the point and assigns to it a coordinate x, y, z. Okay? Now each of these phi's is taking an abstract point to a x, y, z, but these two are doing it in different ways, in different patches. But on the overlap, they are doing it in different ways, but for the same point. The same point in the overlap can go here or it can go there, which means in the overlap region, one point has two coordinate descriptions. We can use that to go from here, the image of that point, back to the point and there, and thereby we get a map from here to there. Now the open set comes in for the following reason. We don't just want to study a point in physics. We always want to study the neighborhood of a point. Why? Because sometimes a particle may be moving and we want to know what is its velocity. That can't be found out by looking at a particle at one point. You have to look at it in an infinitesimal region in order to differentiate it. So in order to do calculus, this stuff is required. And the stuff does the simple job of transforming the study of a complicated manifold into the study of ordinary calculus, because if the coordinates here are x and the coordinates here are x prime, the only thing you'll ever need is the chain rule to transform functions of x into functions of x prime. You already used it once, we'll use it more today. You don't need anything more. Okay, so all the concepts you learnt in calculus, like differentiation, integration, and so on, can all be done in a usual setting, but of course not one variable calculus, it's multivariable because a manifold has multi dimensions. You may ask, okay, maybe it's possible to differentiate, but how on earth can I integrate a function over the whole manifold? Well, that's a whole story which we are not going to discuss in this course. But just to tell you, if you are curious, I'll integrate it over this patch using this image. I'll integrate it over this patch using this image. I'll subtract the overlap which got double counted, and I'll keep doing that, adding up over all patches and subtracting all overlaps till I get a number for the whole manifold. That will be the integral of the function through the manifold. There was a question there.
So this mapping is invertible from O1
Yes,
And we can go from, so it is taking a point to point correspondence.
that's correct.
What will carry the information of the curvature of?
Yeah, that we have yet to see. We have not yet got any information about the curvature.
Okay, and we can never know about
The-
the boundaries
Boundaries, what do you mean by boundaries?
because we have defined an open set, so
Yeah.
we can never go to the
Yeah,
edge
so
of the.
so the all that it means is that on this set I can't go to its edge, but certain, and therefore I can't go here also, but this shaded region is away from the edge of O1 as well as from the edge of O2. In the shaded region I can travel freely.
That was my further question. That how do you like? Is there a then a region defined for an overlap and there is no boundary because it is open?
Yeah, it's not that there's no boundary, there is a boundary, but the region is defined to not contain the boundary. We just don't say that the boundary elements are in that region.
I think
Yeah.
what she's asking is, can the topological space itself have boundaries?
Yeah, that's a whole other story. So topological space can have boundaries and then the definition of open sets changes. So that's a little more complicated. Here we keep thinking about the sphere and soon we'll have to go to other manifolds. For example, our universe is a manifold and it's quite a complicated one. But for now, I'm keeping the discussion as informal as I can, just telling you the precise meaning of the things we were doing. Yes.
Do both of the patches have to map to the same RD or can it
Yes,
be
good. Thank you. So it's very important that both patches map to some subset of RD for the same D. And that D is called the dimension of the manifold. You can't have one patch mapping to R2 and the other patch mapping to R3 because in the first place, these phi maps which are required to be invertible won't exist. You can't have continuous invertible maps from R2 to R3.
Is there going to be always the overlap between two patches?
There doesn't have to be an overlap between any two patches. So look in this system, here's O1, here's O2, here's O3. O1 and O3 don't overlap, but O1 and O2 overlap and O2 and O3 also overlap. The important thing is that this whole thing should cover the space without leaving out any points. How they overlap is entirely up to you. For example, as we said yesterday, one of these can cover the whole space minus just 1 point or 2 points, and another one can cover the whole space minus some other 2 points, and therefore the overlap is almost the whole space. Yes.
What are the constraints on the value of D?
None. This defines a differentiable manifold of dimension D. It's a positive integer.
No, so given some open sets,
Yeah.
what constrains me to use a particular D? Can I use a bigger D or smaller D?
You can try, but you won't find these phi maps unless your D is chosen correctly to match your manifold. Each manifold comes with a concept of a dimension, and the dimension is just the number of independent directions on it. So on a sphere, there are 2 independent directions at any point. Okay. Concretely, think about a sphere. If this is a sphere, this is a disk pasted on the sphere. Okay. In that disk, there are 2 directions. If I just want to call them theta and phi, then theta and phi make up a subset of R2 because as theta and phi vary in values, I'll get some 2-dimensional space. These Euclidean spaces are utterly simple. They are nothing but the space of many variables, which are all independent. The variables don't have anything to do with each other. So theta and phi vary freely over a finite range. You will never reach theta equals 0 or 2 pi because you're going to choose these patches to cover some finite small region in general. Yes.
But I can describe a sphere in R3 with constraints, right?
Yes, but with constraints, that doesn't. So this is a 1-to-1 map. Okay, I should have said 1-to-1 onto map between this patch and a corresponding image in RD. If it's 1-to-1 onto, then there cannot be constraints, and I can't have any higher or lower dimension. You can't have a 1-to-1 onto map from R2 to from R2 to R3 because it just won't be onto. Yeah.
So the boundary of O1 can be reached in OP.
Yes, absolutely. So the boundary of O1 can be reached in some open set, but it won't be O1 itself. After all, when I finish covering the space, there will be enough covers so that this boundary region of O1 is included in many other charts, but not in O1. It's
So like every point can be reached.
every point can be reached, of course, because otherwise I don't have a manifold. I have to define a manifold such that I can study the geometry of any part of it. There's no point excluded. Okay, so this very complicated now looking diagram encodes what is called a differentiable manifold. And this differentiable manifold comes with coordinates in every patch. So the chart, a coordinate chart, is the open set O1 as well as the map phi I of UI. This pair together, and technically also people include the dimension, but I think that's sort of obvious. So this pair is the chart. So it's a choice of some part of my manifold and the coordinates on that part of the manifold. These two things. Yes.
The dimension goes into the definition of the manifold.
Yes.
Or is it an outcome of the charts that are defined?
Well, you can think of it either way. If there exist charts which map to RD, then that is the dimension of the manifold. If
I
the,
can always extend it to RD plus 1. when
you
take
can't
the
because
extra-
it's 1-to-1 and onto, so you can't. The 1-to-1, see, 1-to-1 is very difficult. Given two numbers xy, can you use them to cover three numbers xy and z in a 1-to-1 onto way?
I can take the third one to be always 0.
No, then it's not 1-to-1. I mean, then it's not onto.
Yeah, right.
It's either not 1-to-1 or it's not onto. If I take the higher to the lower, it won't be 1-to-1, it will be many-to-1. If I take the lower dimensional to higher, then it won't be onto. Exactly. So I can't do that. So D is unique. Yeah. So this is a chart. Okay. So all we've done is succeeded in setting up charts with coordinates, but we haven't mentioned anything about distance, which we discussed extensively yesterday. So now at the next step, so collection of charts that cover the space which I'll call M with differentiable functions. Differentiable simply means one can differentiate them. The function doesn't become so bad that after I've differentiated once or twice, it's no longer differentiable. There can be functions like that. Functions which have some cusps or some sharp bends and so on are not differentiable at those points. In physics, we like everything to be as smooth and as differentiable as possible because we never know when it will go into some equation, and that will be a differential equation almost always. So we like things to be differentiable. So with differential functions between charts, between the image phi I of UI, phi I of OI. These are the images. The images, as I told you, they live in the Euclidean space, and going between them, we have some functions like x of x prime or x prime of x. Those functions are taken to be differentiable. That's important. Having done that, we get what is called a differentiable manifold. It's quite possible that my description today will also make a mathematician cry, because you should really write fill in lots of details, but I think I have captured the essentials of a differentiable manifold. The point is that there have to exist functions between every image of every chart and the image of any chart that overlaps with it. Okay? And these functions have to all be well behaved. And the very surprising thing is that on a given topological space, sometimes you can have more than one differentiable manifold which are not compatible with each other, which means that these transition functions, as I call them, of one choice of charts is not differentiably compatible with the transition function for another choice, and people have got Fields medals for discovering these things. But fortunately in physics there is one sort of standard way to get differentiable manifolds, and that seems to work always. So we as physicists don't need to worry about these so-called exotic differential manifolds. Yes.
Does the definition of differential manifold include those functions phi and
It doesn't yeah, good question. So does it include the specification of those functions? No, it does not. In fact, this is the point. I may define one differential manifold and you may define another using different sets of functions. How will we check if we arrived at the same differential manifold? It's very simple. We'll take all your open sets and all my open sets and we'll add them together into a bigger collection of open sets. Okay, and all your maps and all my maps, and we'll add everything, and at the end of it we again have a chart. We again have what is called an atlas, which is a collection of charts. It may be very wasteful. I might be taking yours and mine and I don't need so many open sets, but it doesn't matter as long as all of them satisfy this property that on overlaps the function between one chart and another, which could be two charts of my definition or two charts in yours or one chart in mine and one in yours. I can compare all of them. This is the way to compare. If everything fits nicely, then it's the same differential manifold.
I can have like infinitely many.
You can have infinitely many charts. There's no law against it and there's no price for charts. They are free. Unlike ChatGPT, charts are free. ChatGPT is increasingly becoming useless unless you pay for it, as I'm finding. Anyway, today I had a huge fight with it because it kept giving me formulae in LaTeX. And when I said, please can you give human readable, it simply removed the backslashes as if that makes it. And then as usual, sorry, I'll do better next time. And it doesn't actually. It reminds you of the most annoying people you know. Anyway, good. Any more questions? Yes.
Does the topological space have to be metrizable?
Metrizable or not up to this stage. It has to be metrizable to do the next thing which we are about to do, which is to define a metric. Yeah. Now, given a differentiable manifold, we assume we already have these charts and they all come with their map to some coordinate system. Then we can introduce a metric. And when we do that, we get what is called a Riemannian manifold. It's the next step after differentiable manifold. All the things that were there are there, plus one new thing, the metric. Okay? And this means that I have a matrix valued function Gij of x with a definite expression of, so first of all it is symmetric, invertible and smooth and given on every coordinate patch. So in other words, what I can do is take the open set of my manifold in one open set, transport it to Euclidean space. There I define the function Gij of x. As you can see, Gij is just a multivariable function. It just has arguments x, which are x, y, and z, or r, theta, and phi. It doesn't matter. Any number of variables, but that number will match with the dimension of the original manifold. And they're all independent. Okay, so it's a function. And so I've given it on every coordinate patch such that on the overlap, on any overlap of two patches, we have G prime Ij of x prime is equal to del x k I L J G K L of x. So this gives me the function G prime Ij of x prime if I know the function GKL of x, and because these factors are invertible, I can as well go get this function starting from that one, always in the patch. you can see that some of the tension some of you had yesterday is relieved by realizing that we never go out of the patch, we never go out of the overlap of two coordinates when discussing this. Okay, this equation is only valid in that shaded region where two coordinate systems overlap. It doesn't make any sense if I'm away from that shaded region. So it's in any pairwise shaded region I need this. And those regions I can pick to be as easy to handle as possible, so that I never have to worry about the going back and forth in this. Everything is back and forth. Everything goes in both directions. Neither one is more privileged than the other. Showing that actually no coordinate system is better than another one. Maybe more convenient, but none is more fundamental than another one. It's very democratic that way. Okay. And this should satisfy the triangle inequality, which we discussed, I think, yesterday. So if dAB is the integral from point A to point B of ds, then dAB plus dBc is greater than or equal to dAc. And these are all real, these d's are all just some real number which I get by doing that integral. Yes?
We saw in special relativity that the interval could be negative or even.
We haven't got to relativity. We are doing spatial differential geometry. I told you yesterday we are now trying to review Riemann's work of the century prior to 20th.
Okay, but it doesn't obey the laws of like a matrix
Indeed.
function, right?
Yeah,
Where
we'll get to it, yes.
Why do we need the metric tensor to be invertible?
Why do we need it to? You'll see as we go along. But there are many good reasons. If it's not invertible, let's see. Yeah, we'll see as we go along. I'll highlight later. Yeah.
Another question.
Yeah.
So this metric, are we defining on the topological space itself, or are we defining on the functions?
It defines a metric on the topological space, but by transporting the metric, the functions, these functions. So when you say these functions, they are defined only on the Euclidean space. But ultimately, the collection of all these functions over all coordinate patches of the manifold defines a metric on the manifold, because I can then calculate this thing on the manifold itself. It's a tool to calculate. It originates from that. Good. Okay. Now, we are going a bit slower than I had planned, but okay. Now, obviously, on a manifold, I would like to define vectors. We've only defined one tensor so far, which is the metric, but I might have vectors. Yes.
Would Riemannian manifolds for every single for two different patches be unique to those patches?
No. What does that mean?
I mean, for example, you're calculating the Riemannian manifold for two patches.
No, I can't calculate a manifold for two patches. I have a topological space. I have a collection of patches that cover the whole space. They may be two or they may be more than two, but they need to cover the entire space. Okay. Now on each patch, I specify a coordinate system by these 5 maps. And then on overlap of any two patches, I specify a transition function by the change of coordinates. But there's still only one topological space and one differentiable manifold I get at the end of this process, not many. From one topological space, in principle, I could get many differentiable manifolds. But each time I do this procedure, I end up with one. And as he asked, if two people end up with two different differentiable manifolds, they can compare them, and typically they'll find that they're actually the same. It's not very easy to put more than one differentiable structure on a topological space in practice.
So all transition functions are unique.
Transition? What do you mean by unique? What is the
Like they're different.
different? Unique and different may
No,
not.
I mean like they're not different, Baba.
They're not different. From what?
Like to each other, because as far as what I'm understanding, you have two different patches. Like you can have it like n different
Yes,
patches covering
yes.
the entire manifold.
Yes.
And then the transition function is like unique to those two patches that you're using.
Yes,
Their overlap.
it's unique to that overlap, and it comes as part of the information that I gave for the patches, because each patch comes with its map to Euclidean space, and therefore the overlap comes with two maps. And then phi 1 inverse phi 2 is a map from Euclidean to Euclidean space, and that is my change of coordinates function. Okay, so it's obvious that we need to talk about vectors in Riemannian manifolds, because we talk about vectors in flat space and in Euclidean space, and everything we are doing here is supposed to generalize what we know to more general systems such as the sphere, or maybe more general manifolds. That was the whole approach. So you might know that spherical geometry has been studied for centuries and millennia in ancient Greece, in ancient Indian subcontinent, in ancient Persia, but only spherical because that was the thing people could talk about, the S2. Once we make it algebraic, we can talk about more general things. But we certainly want to transport our physics notions to these more general spaces, because, for example, I can imagine a free particle, and we'll actually do that soon, on some Riemannian manifold propagating in a force-free way. And we can ask what trajectory it will choose, and things like that. And those can really be, those can actually be realized. Imagine making a spherical kind of ball in my lab and put a particle on it and somehow make sure the force of gravity doesn't act on it. Maybe send it to space so that it's weightless. And now it will move, and does it follow Newton's law, or what does it follow? It's constrained on the surface of this space. Other than that, nothing. No force is acting on it. What does it do? That's a physics question, and that physics question can actually influence real experiments. So it's worth asking how to do physics on a curved manifold, on a curved spatial manifold, and that's what we want to do now. So the first thing is, of course, we can have vectors ai of x, and we need to decide, so it's just a multi-component object but with only one index, unlike the metric we had. And we need to ask what transformation property this should have across coordinate patches. So what is the relation between a prime I of x prime and ai of x? And the answer can be found by a very simple idea. First, define the norm of a vector by saying that the squared norm is just equal to ai, aj, gij. So we have already been given a metric. So we'll just use it to contract both the upper indices of a vector, and we'll call that thing a squared and take its positive square root to get the length. Okay, it's a very natural thing to do, and now you realize that, well, the length of a vector is something that we would like to be a scalar or an invariant across coordinate patches. So A must transform in the way which cancels the transformation of G. Okay, so once we start to impose these basic conditions, everything acquires a transformation law across these patches. Yes.
So is the vector defined locally in one chart?
Yes, again the same story, that the function ai of x, which actually mathematicians call the components of the vector, those are defined only in the chart where x is a coordinate. But in another chart, they are defined, they are different functions, but everything is patched up so that there's a unique vector field all over the manifold, just that my description of it is chart by chart.
And they're connected by invariant norm.
They are all, yeah, so they're not connected by an invariant norm. The norm can also change across the manifold. It's a scalar function, so it might, but it'll be the same in all the charts.
Okay.
But it might change from point to point. It might shrink somewhere and increase somewhere. That it can do. Yeah. And we easily find that a prime I of x prime, and these are exercises for you, is dx prime I dx a of x. This is a, you find this by requiring this to be scalar or invariant. What happens when A transforms? Each A cancels one factor in the transformation of G, and therefore the whole thing is invariant. If you remember, the G transformation had x upstairs and x prime downstairs, It was a covariant tensor. These are contravariant vectors. So this is a contravariant vector. Now there's nothing that special about a contravariant vector. We can in fact lower its index by simply defining a lower I to be the contraction Gij. This is not a transformation of different across different coordinates. In the same coordinates, I just define the lower index object to be Gij times the upper index object. You can verify for yourself that this one transforms differently from the upper index one, and in fact it transforms like just one of the indices of G. This is why the index notation is so useful. Just by inspection you can say, okay, lower J and upper J are contracted, so the transformation of that index can be ignored. It cancels. I on the other hand does transform, and that transformation is inherited by AI. Okay, so if you start thinking like that, formulas in Riemannian geometry will start to make sense. Now, this function can be a completely different function from that function because Gij is a function in general. It's not some constant thing. So we can start with a contravariant vector whose components look like something, make it covariant and its components look like something totally different. Not some trivial change. The difference between the covariant and contravariant can be a lot when you look at it, but both carry the same information because if we have since G is invertible, we define Gij by Gij Gjk is delta Ik. This is the matrix inverse. This is just the equation in algebra for inverse of a matrix. M inverse M is 1. But when it's inverse, we put its indices up. So this equation is natural. And you can also verify that this identity matrix is invariant under coordinate transformations if I transform its lower index as a covariant index and upper index as a contravariant index. So actually, it's a very special matrix, yes.
Can we see that the covariant vector space is a dual space?
Yeah, so mathematically it is a dual space, but for physics we don't need to. I think it is too much to go into that from a physics perspective. We don't need that. Because the dual space thing is important if I don't have a metric, because then I don't have any other way to relate the covariant and contravariant guys. Once I have a metric, I can just go back and forth between them, which identifies the space and the dual space in your language. So I don't need to talk about it anymore. So why can I go back? Well, now I can show that the original A upper I is nothing but G inverse, which I write this way, times this. Okay, so you see the back and forth. I can go from a contravariant vector to covariant, and using the covariant I can go back to contravariant, and therefore they carry the same information as long as I have a metric. So the only information added in doing this is the information of the metric, but I can always add it or remove it. It's completely removable because the metric is known and invertible. Okay, so this is what is going to be a vector on a manifold, and it's more general than anything you have encountered so far. But actually there's a special case of this which you have encountered. Supposing I had a very trivial manifold, and supposing all I did in going from one patch to another was to keep the same patch, the same open set, but change my map so that one is rotated with respect to the other. So imagine I had a very trivial manifold and I just had one patch over here, and I had one map phi1 to x and y and another map phi2 to x and y, like that, rotation. And suppose this was itself Euclidean space. We never said it can't be. In general it need not be, but it could be. Okay, so very trivial change of coordinates. So what is the change of coordinates? It is x prime I is equal to Oij xj. We've seen that, where O transpose O is equal to identity. This is a very special change of coordinates because it's linear. O is a constant matrix. The O depends only on the angles of rotation, doesn't depend on where I am in the space. It's a constant rotation. So this is rotated everywhere in the same way. This is this way everywhere in the same way. So this is my change of coordinates. And now I can easily see that if I have a vector A prime I, under this change of coordinates, it will just transform like this. And I would suspect that you have seen this equation multiple times in physics, because in classical mechanics, in quantum mechanics, in electrodynamics, anything where you rotate a vector, whether it's electric field or magnetic field or any other vector, acceleration, velocity, this is how they rotate. If you want to write it out, it is cos theta, sin theta, minus sin theta, cos theta in 2 dimensions, but this is the abstract form of it. And so change of coordinates in particular can be a rotation, and that's a very simple one because O is a constant matrix. In this case also, the metric in the 2 frames will be related by a constant matrix, because all we are doing is taking different linear combination of the components of the metric going from one frame to another. So that will be a special case. So this is just a very special case. And the beautiful thing is that we can actually deal with the general case, which is any invertible change of coordinates. We have a formalism which tells me how vectors and tensors transform. I suppose it's almost obvious by now how the most general tensor I can ever think of transforms under a change of frames. So let me try to write a tensor I1 up to Im, J1 up to Jn, and put a prime and put x prime, let it depend on x prime. So now I would request the class to please dictate to me what I should write next. How do I relate this tensor to the same thing in the x coordinate system? What's the rule? Good. So go index by index and write a factor for every index. That's the first thing. What is the factor for this index? It's del x I1 and it's got a prime by del x, let's say A1. Then I keep that repeating that till I get del x prime Im by del x Am. That takes care of all the upper indices. For the lower, I do the same, but I have to reverse which one is up and which one is down. So I have del x B1 over del x prime J1 up to del x Bn over del x prime Jn, and then T A1 to Am, B1 to Bn of x. And whenever you write such an equation, you can always verify that it's correct. How? At least you can easily find mistakes you might have made. Check that the indices match on both sides. The free indices here are I1 up to Im up and J1 up to Jn down. If your right side has any more or less indices, you're in trouble. This can't be an equation. And if your right hand side has the i's down instead of up and the j's up instead of down, you're also in trouble. And so you have to check here, and what you verify is, for example, A1 is contracted, it's summed over. All the a's are summed over, all the b's are similarly summed over these, and what is left are the i's and the j's. It's very simple. It's much simpler than you probably ever thought a tensor would be. It's the same rule as for vector, treating every index as its own thing. Okay, and this gives you a complete specification of how geometrical objects transform under change of coordinates, and we need that change of coordinates in order to define a non-trivial curved manifold. In general, we won't be able to define the manifold and do anything on it and make a metric on it without having those transition functions. So we need to know how every physics quantity transforms from one of these patches to another. Yes?
I had a question related to the vectors. So
Yes.
the vector space, if we talk about, how can we exactly show that it is a vector space, because it needs to satisfy closure and the existence of an identity, and say for one patch
Yeah.
in some coordinates we have
Yeah.
an identity,
Good.
and then in another patch that could look very different. Then how would
Yeah.
the
No,
space
actually,
be-
in a vector space, the identity is called 0. It's the 0 vector.
yeah.
And the 0 vector, as you can see from this general transformation rule, if the tensor is 0 before, it's 0 after. So identity is there in this, is the same in all patches,
And
to answer
the
your question.
closure relation-
Yes. So closure, it's, you see, the point is this transformation is linear in the tensor itself.
Okay.
So if I have two tensors T1 and T2, I mean, why go to the complicated case? We can do it in the simple case. I'm glad you brought it up because it's a valuable check. So if I have A prime I equals del x prime I del x A, and I have B prime I equals del x prime I del x A B A, then A prime I plus B prime I, sorry, is equal to del x prime I A plus B. Linearity ensures that. So that they do form a vector space. I should say that a vector, abstract vector in mathematics just forms a vector space. These, what we call vectors in physics, the mathematicians will call vector fields, because it's not just a vector at a point. It's a family of vectors which vary smoothly over a whole region. That's called a vector field. And mathematicians have a different description for the covariant ones with the lower indices, because they don't in general assume that a metric exists. But since we have a metric, we don't need to do any fancy things to define the other kind of vectors. They are also vectors. The metric does the job of allowing us to go back and forth between them. Okay. Now, I'll stop here, but this might have looked really dry. But if you realize, first of all, it's a good thing to learn for any physicist, because geometry of, as I have said before, geometry of your lab setup can be a thing. It depends on your lab setup. Okay, people have tips on their atomic force microscopes and so on, which might be spherical or might be elliptical or might be any other thing, and actually calculations in how the physical forces work or how the experiment works do depend on the curvature of the tip of a probe. So even a very, very practical thing like using a microscope tip to study a sample can require some understanding of differential geometry. Now, of course, nobody insists that everybody who does those experiments needs to know it, but I think it's good if theoretical physicists or theoretically inclined or trained physicists know it for its own sake. The excitement is that soon, in fact in the very next lecture, we'll be able to transport many of these into a framework which was not imaginable till Einstein did his work, where we add time into the coordinates. And we make manifolds not of space but of space-time. All the physics changes completely. We are talking about we'll be talking about points in space-time rather than points in space. We'll be talking about curvature in space-time rather than curvature of space. And curvature in space-time is bizarre. It means that a coordinate x and a coordinate t can have some curvature between them. What does it mean? Well, actually, you know some example of it. It's nothing but a generalization of Lorentz transformations. It will turn out that actually the curvature relates to the acceleration of different frames. So, and what we call the transition functions, the change of patch over here, will go into change of coordinates across different non-inertial frames in GR, general relativity. I'm just announcing this. I'm not teaching this now. It will be done not next week after next, because next week is the quiz on Thursday and Friday is a ICER holiday. So week after next we meet again.